How goes it? Eh? It goes. Have any questions on anything before we get going into stuff? Got a little homework action here for you. I don't know, what would you like it to? Never is not an option. After graduation is not an option.
The day before graduation.
Wednesday is the day before Easter break because we don't class that Friday. So you want to just do it Wednesday? Whatever that is, the 17th? Does that work? We're going to leave a bridal shower that weekend.
I do.
See it wasn't on there. I just happened to see bridal showers. Like, oh, all right, cool. All right. Let's do another example like we talked about last time with the Wilcoxon statistic. What did we do last time? Did 8.5-6? Okay. Let's do 8.5-7 then. So we've got, hey, I'm going to remember to zoom this in before we start. Oh, hey, apparently to 392%. God. Me and technology this semester has not been good. It's Sarah's fault. Where's Haley? Well, the best part about Nuage is he was in advanced calc. I saw him leave.
I just saw him walking out when I was walking.
I would ask where Nuage is, but it's more common that he's not here than he is. So maybe he watches the videos and he'll hear this.
I hope he watches the video.
I told him there was a testing here on Friday.
Oh, did you?
Got Kelly and Sydney to play along.
It's funny. I like it. All right. So 8.5-7, we got weights of bags of carrots. And we're going to test whether or not the median is greater than 1.14. So remember with our Wilcoxon statistic, we are looking at that Wilcoxon sum, where we do the signed ranks, and I believe I referred to those as V sub i's last time. And if I use W as the statistic, then we divide by the square root of the variance of those things. And remember, the variance you can show is, what we did last time actually, it's n times n plus 1 times 2n plus 1 all over 6. That's the statistic. And then we said that's approximately normal, so we can check its p-value against a normal distribution with mean 0 and that particular standard deviation. Or in reverse, like we do with z-tests, you can also find a critical value and compare it to a critical value. So remember that these V sub i's are your signed ranks. And again, what we mean by that is we rank each point, each data point, by how far away it is from the median. The bigger that number is, the farther away a data point is from the median, the larger rank it has. That's what the rank part means. The signed part means You'll have it positive if it's above the median. It's negative if it's below the median. And then if we have two that are the same distance from the median, then you just average the ranks. Okay? So if we go back over to the data that's over in that Excel sheet, the 8.5-7, I'm going to type in the 1.14 for our median and just copy it down so I can refer to it. Maybe I'm going to copy it down. There we go. And then subtract across. So we'll do, actually I'm going to do the absolute value of the difference. Because the absolute value of the difference is going to give us the absolute difference of how far away it is from the median. At this point, I don't care what side of the median it's on. I just care about how big the difference is because that's how we're getting our ranks. Okay, so that's why we're doing the absolute value of the difference here. Copy that formula down. I mean, at this point, you could do it by hand, but why do it by hand when Excel will do it for you? So there are 14 items in our list, so I'm going to do 15 minus the rank average. Remember again, the reason why I'm doing the 15 minus part, the rank average ranks the biggest as the lowest rank. It tells you what it ranks from highest to lowest, and we want to rank from lowest to highest. Smaller numbers should give a smaller rank. The rank command in Excel gives you higher number, gives you lowest rank. Because it's saying it's the highest, it's number 1. Okay. So that's why we do the reverse of this. So this is always one more than the number of the data points, so that's why I've got the 15 there to subtract it. So I want the rank average of C1 compared to the rest of the array. And then I want to make an absolute cell reference on that array. That ranks them from lowest to highest. And then again, we want to do signed rank. Each of those ranks I want to give a 1 value to if it's above the mean, a -1 value if it's below the mean. So I can multiply that by the sign of the difference. So of A1 minus B1. Actually, if you're a Latin scholar, which I don't think any of us in this room are, but if you're a Latin scholar, that actually is referred to in Latin, it's referred to as the signum function, and that's where the word sign comes from. Signum is a sign, so it's 1 or -1. So. And then if you plug in 0, you should get 0 out, because 0 doesn't have a sign. I know very little of those things, so that's why I mentioned them when I actually have an occasion to. All right. -2.5 is that first one if we scroll down. So we've got a couple that tied, which you can see. So the -2.5 is saying that those 1.12s both have the same distance below the median. The couple of 10.5 saying that they both have the same distance above the median, the 1.23s. All right. So again, notice the ones that are negative are indicating the ones that are below the median, and the ones that are positive are indicating the ones that are above the median. Okay?
I got different answers on the first two, but then the rest are the same.
You have the same numbers?
Like the first, like I got -3, -2, and then all the rest are the same.
That doesn't make any sense. It's because you didn't start your array at 2. You started your array at 3. See where you're dollar that one?
Oh, so you do all of them?
Yeah, you have to do all of them.
Oh,
yeah.
I thought it was the first
No.
one and then the difference.
No, yeah. You have to do all of them. That's why I was doing that.
Gotcha.
It was really weird that you were getting different
Yeah.
numbers. Okay. Everybody get that one okay? Or get that part okay? Why don't you get different numbers?
No, I got 3.5.
That's supposed to be times, yeah. There you go. Okay. Anybody else? You good?
Yeah.
Good? Good. Okay. Hey, we're not dealing with GeoGebra, so it makes it a little easier to fix. All right, good so far? Okay, so then our Wilcoxon statistic was we sum those things up. So I just want to sum up the D column. Doesn't really matter where you put it, I just need to add it up. Let's put it off to the side because I'm zoomed in so far, going to the bottom wasn't a very good idea. All right, so again, depending on how you set up your problem, you could find a critical value based on the z-score and the standard deviation and figure out how big it would need to be. So if we're doing this at the 0.1 level and you're doing one-tailed, your z that you would be using would be what, 1.28 if it's one-tailed and 0.1? So you could do 1.28 times the standard deviation to get your critical value and compare this to the critical value. Right? Because you could do your critical value for z at that point would be 1.28. Your mean is 0 in these, right? The mean for your Wilcoxon sum is 0. So you would just need to do the critical value would be 1.28 times the square root of 14 times 15 times 29 over 6. Because you do your z value times the standard deviation. You would ordinarily add the mean, but the mean of the Wilcoxon statistic is 0. So I don't need to worry about adding anything there. That would give you a credit if you want to do it. Like I said, if you want to compare it to a critical value, that's how you find your critical value. I'm just going to do a p-value, so I'm just going to plug it into a normal distribution anyway. Okay. But if you wanted your critical value, you could do, I'll label it over here to the side. Critical value would be 1.28 times the square root of 14 times 15 times 29 over 6. So you'd have 40. So at this point, would you reject or not? Is your 67 in the rejection region? Is it higher than the critical value? Not a trick question. 67 bigger than 40? Yeah. So you would reject in this case. Okay. If you wanted to do the p-value, either way, obviously either way works. P-value would be you want to do 1 minus your normal distribution. Your x value is the 67. Your mean, again, is 0. Your standard deviation is the square root of n, which is 14, times n plus 1, which is 15, times 2n plus 1, which is 29 over 6. And we want cumulative. I did 1 minus because if I'm doing cumulative, that'll give me everything up to 67. And I want the tail for the p-value. So I did 1 minus. In these problems, you can do one or the other. You can find the critical value and compare it to the critical value, or you can do the p-value. I personally don't care. You should already understand the connection between critical values and p-values.
So what is that D row? What is that called?
What is what called? Sorry.
The whole D row. Like what is that?
Oh, you mean this column?
Yeah. Our column.
These are the signed ranks.
Signed ranks. Okay.
Yeah. So notice that this -1 here.
Yeah.
It says that this is the smallest value in this list, and it's below the median. below the purported median, I should say. This 7 says it's the 7th smallest value in the list, but it's above the median since it's positive.
Okay. And how did we get the median again? Is it just?
It was given to us. It said we're testing it against the median 1.14.
Okay. So it's like, because I tried to do like the median function and it wasn't.
Yeah. Is okay? So again, even with the p-value, see here we see that we reject. I did not do the unit correction that they talk about in the textbook. Again, it depends on what textbook you look at of whether or not you need to do a correction. If you do a unit correction, you would subtract 1 off the 67 first before you compare. That's all the unit correction means. The reason for that, and I don't have a picture of it because I was too lazy to make up a picture and I didn't feel like copying out of the textbook. There's one in the textbook. The reason for that is when you look at the graph of the distribution, your bars at the top of your distribution for the Wilcoxon sum don't ever get to the top of your normal distribution. Unlike the binomial where you've got it kind of balanced on both sides, so you use a half unit correction. In that case, when you're doing the continuity correction, you use it in half because usually the bars are across the normal distribution, is a little bit below and a little bit above, so you use that half unit to basically like a midpoint rule idea, right? We talked about continuity correction for binomial before. And you actually see that on some of the actuarial exams, by the way, the continuity correction. This one you do a unit correction because the whole freaking bar is underneath the distribution. So you subtract 1 off of it to get a correction for that. Again, it depends on what book you look at. And it's only really that important if you're close, right? And if you're that close, take a larger sample and see if you can get it better anyway. I mean, that would be what you would do in practice. If you're that close to thinking, oh, I could have rejected, but this unit correction says that I can't, well, then get a few more data points and see what happens. And that's what you would do in practice anyway, which is why I'm not as worried about it and why I would suppose that other texts aren't as worried about it. Does that make sense? Okay. So one other type of test we would do against medians is, say we've got a list of 2 different sets of data, and we want to know, are their medians equal or not? Okay. So there's a couple of different ideas behind that. Are they paired or are they not paired? If they're paired, then you would just subtract the pairs and see if the median's 0 or not. Okay? And that's what you're asked to do in 8.5-5. It's one of the homework ones I gave you. If they're paired data, then all you would do is just subtract the pairs and compare the median to 0. Okay? So that's not hard. You just have to subtract first. Okay? Now, if they're not paired, what do you have to do instead? Well, it turns out that if they're not paired, what we end up doing is basically pooling them and seeing what happens. So if we do that, let's write this down. So let's say we have let's say we have an x1, x2 out to xm. Not xm because we're using m for median, xn1. And we have a y1, y2 out to yn2. We have 2 different sets of data. Okay. We're going to, and we want to test, is the null hypothesis is that the median of the x's is equal to the median of the y's. The alternative could be 2-sided or 1-sided. It doesn't matter. So that's our null hypothesis that we're testing. All right. So the idea here is to first rank order the whole list. So you would take the, you take your x1, x2, x3, xn1, y1, y2, yn2. So you get this list of n1 plus n2 items, right? You rank order that. What I mean by rank order is what we did over here. That column D is your rank ordering. We put signs on it, but that's the rank ordering. Okay? But all we're interested in here is the sum of the ranks. We're not worried about whether they're signed or not in this case, because we're trying to compare it to just the x. Okay? All right, so we would expect that if the medians are different, so in particular, say we're supposing that the median of the y's is bigger than the median of the x's, then we would expect that the sample of y's should be above the sample for the x's, so the median of the ranks should be shifted to the right. In general, the ranks of the y's should be bigger than the ranks of the x's. Right? So just to write that down, oops, maybe. Thank you. If the median of the y is greater than the median of the x, then the ranks in general, the ranks of the y's should be bigger than the ranks of the x's. Oh, for heaven's sake. Why can I not write today? I say that a lot, don't I? Maybe I just can't write. Does that make sense why that should intuitively be true? If you've got a higher median for the y's than you do for the x's, then from a probability standpoint, if you're taking a random sample of your y's, again, half of those you would expect to be above the median for y, right? In general, those should be bigger than the x's because, again, the half of the x's should be below the median. Right? So you should have high, it's just in this in general, but think about half of them you would expect to be above the median for the y's, and half of them you would expect to be below the median for the x's. Well, then all of those y's, for half of them, should definitely be bigger than half of the x's from an expected value standpoint. And then the rest should be, well, even though you're taking some of that are below the median for y, those are probably going to be bigger than some of those for the x's anyway, because the median for the x's are smaller. So you would expect more y's to be above x's. So the rank should be higher in general. That's the idea. All right, so we want to get a statistic based on that idea. To do that, again, we're going to let W be the sum of the ranks of the y's. Now, they don't derive this in the book, and we're not going to derive it either. The expected value of W is your N2, the size of how many Y's there are, times N1 plus N2 plus 1, all over 2. And the variance of W is equal to N1 times N2 times N1 plus N2 plus 1, all over 12. So then we're going to test our Z statistic here will be W minus the expected value of W. Ooh, that is an ugly plus 1. And then all over the square root of the variance. This is approximately normal if your N1 and N2 are at least 7.
Does that say W minus N2?
W minus N2? Yeah, it's an N2, yeah.
Okay.
It's the expected value. It's just this written there. Yeah. We're doing our standard Z-score. Subtract the mean, divide by the standard deviation. So again, we're not going to derive these, although notice that they kind of look uniform, right? The denominators remind us of uniform. The denominator in the uniform distribution is a 2 for the expected value and a 12 for the variance. Discrete uniform, I should say. No, it's also in the continuous uniform as well, but so kind of looks like a uniform distribution idea. Notice that the statistics that we're doing here are distribution independent. When we're doing these tests on the medians, that's why they're called the non-parametric tests. The median is not a parameter. The median is just a measure of where the 50th percentile is. All right, so let's see if we can do one with this statistic. So let's do 8.5-8. (8.5-8) has the weights of pills in their packaging when the packaging is good versus when it's defective. So the X is when it's good, the Y is when it's defective, and they're both measured after the pill has spent a week in a chamber containing 100% humidity and heated to 30 degrees Celsius. So basically the Midwest in the summer. All right, so I want to calculate the ranks of the Ys. Column B is the Ys. So this is the defective packaging compared to the overall ranks. In general, if we were doing this by hand, that wouldn't be very much fun. At least I don't think it would be very much fun. Okay? Because you would have to first sort them all as one big list and then go back and pick out the Ys. But when we've got something like Excel, we can do it very easily, especially since I got the X's in one column and the Y's in the other. Because we're going to use that rank average command again. I need to do it in reverse again. How many total data points do we have? 24? Right? Do the X's plus the Y's? I got to reverse it. So I need to do 24 minus because I got to do... Remember, it ranks from highest to lowest, and we want lowest to highest. Okay? So 24 minus the rank average. Sorry, let me zoom in again because I'm stupid and can't remember to do it. Ever, apparently. 25, sorry. Number of data points is 24. I want to subtract it from 25, so I start at 1. If I subtract it from 24, I'll start at 0. Not that it hurts, it just will start at 0. I want the rank average of the y's, so that's B1, compared to the entire set. So I just need to highlight the entire array. And then absolute cell reference the array. When we copy this down now, it will only rank the y's, but it will be relative to the entire list. Because I put the entire list in the array. So I hit enter and I copy down. There we go.
That's the ranking.
That's the rankings, yeah.
So another argument in there is order, and it says ascending and descending.
Oh, is it another order?
Yeah.
Oh, so I could just change that instead?
Yeah, I think so.
Oh. Did you try it?
No, I didn't try it.
Oh. So basically you're correcting me without knowing if you're right or not.
I don't know if it would work, so I was asking if you knew that was there.
I did not know that was there. Because I
I
didn't.
accidentally hit comma, and then it said descending or ascending. You put a 0
Yeah, it
or
worked.
1.
Oh, it does say order on the end. I never paid attention to it. I couldn't have told you that it was even a comma there. It looked like a period to me. So I just ignored it. Well, thanks. Well, that makes it a lot easier. Okay, so we want... So if I do this... Stop it. Oh, shoot. Rank average. And then I want B1 regard to the whole array, and then absolute, and you said there's another, oh, yeah, we want 1. What do you know? Okay.
Learn something new every day.
I did learn something new today. Thanks, Sydney.
Yeah.
At least I wasn't wrong. Saves a couple of keystrokes. I mean, the other way works as well, but cool. I literally did not even notice that was there.
Yeah, I didn't notice it either, but I hit comma on it.
And it popped up? Yeah. Okay. That's... Okay, cool. Anyway, what do we want to do with these now? What do we want to do with the ranks? What do we do with the signed ranks? Add them up, yeah. So that's exactly what we want to do here again. We want to add those ranks up. Seriously, I did not even see the word order in that thing when it came up. I didn't. I just... whatever. It's not like you can't just adjust it. So that was why I just figured that they only the one in there because you can just adjust it and get the other. But thank you. All right. So this is your statistic. That's what the 205 is. That's your Wilcoxon statistic. Or, this is also called the Mann-Whitney-Wilcoxon statistic. I had to look it up, obviously. All right, so then we want to compute a z-score for that. So remember the expected value, I'm going to put the expected value over here just so we can see it. The expected value, again, is the number of things that are in your y column times the number of overall things. Oops, I need a parenthesis in front of this. The number of overall things plus 1, and then over 2.
You click on that again.
Sorry. I mean, you could have just done it by hand, right? You should be doing 12 times 25 over 2. Because remember, the formula is the N2, so that's the number of the Y's. Now I was just using, if you had a bigger data set, you wouldn't want to count it by hand. That's why I was just showing you the Excel commands. And the things that you're doing for homework, you can count it by hand pretty quickly. Well, especially since I can see how many there are just typed in Excel. Okay. But it's number of Y's times overall things plus 1 over 2. And count just counts whether or not there are numbers in the cell, if I remember correctly. Count counts the number of things in cells that are numbers, and count A counts the number of things that are in, it's just the non-blank cells in the array. So if you're trying to count things that actually have something in them, you would use count A. If you're looking for the count, that was just counting how many numbers are in an array, you use count. Or just count it by hand. You're going to use the numbers. All right. So anyway, the whole point of this was that the expected value is 150. The variance is number of x's times number of y's times 1 more than the total divided by 12. Might have been easier to just put the counts in somewhere else and reference them, but I already typed it now. I'm sure Sid will have an easier way for me later. So far, so good? All right, so that's the variance. So if we want the z-score, then we would do our f2 minus g2, and then divided by the square root of h2. So I just did the Wilcoxon statistic minus the mean and then divided by the standard deviation. So you're going to click on it again, or I'll click on it again so you see it. Make sure I have that in right. We're going to get these other TVs working again, so we'll of course, if I zoom in, then it's not so bad. All right. You can tell by the z value. You can tell by the z value that we're going to reject regardless. But the z value over 3 is going to be a rejection no matter what. Well, unless you want a really, really small significance level. So we're definitely going to reject. So we would say that the median for the y's is bigger than the median for the x's in this case. We can get a p-value again by doing, I've got the z-score now, so if we did the normal distribution, I could do normal standard distribution, that's what the dot S is, and I don't have to type in the mean and the standard deviation. I can do, I wanted to do 1 minus that anyway. I want to do 1 minus that anyway. Norm.s.dist is standard normal, so you don't have to type in the mean and the standard deviation. And since we already did a z-score, that is standard normal.
So you knew we'd reject because the z-score was high?
Mm-hmm. And or the p value is very low, which is what we just computed here. That makes sense? Do you want to do one more like this, or are we okay? I'm happy for either. I'm telling you, I'll let you out 10 minutes early if you don't want to do another one. Are we good? It's not too bad. Of course, you have the video to go back to. You know, the stellar, high-quality videos that I make. All right. So you got homework. And then another reason why I'm letting you out early is 10 minutes is not nearly enough time to start the new stuff that we're going to do. Because there's a lot of conceptual stuff that we're going to be doing next. It's going to be mostly theory and a lot less doing things on Excel. So it's not worth trying to start it in 10 minutes. So, all right, have a good one. We will see you on